Okay, this time we're going to be talking about optimization and what the derivatives do. What are their role? And I'm talking about first derivative and second derivative. And use and understand the application of the first and second derivatives for solving optimization problems is the name of the game in this. So I know you can see this for yourself, and I know you know how to read, but I'll just quickly reiterate these things here about optimization, which if you're watching this video in the correct sequence, this should not be an introduction to optimization. That's not the purpose of this video. You've already seen it before. Otherwise, go back to one of my earlier playlists, my earlier units, where I introduce optimization. But from your previous work, you know things need to be minimized or maximized. Okay, so it depends on the situation. Okay, so manufacturing cost or energy consumption might need to be minimized. The other things that might want to be maximized, made as big as possible, are things like revenue or profit. Okay, so there's lots of examples. Either way, it's called optimization. We're trying to optimize things, and the derivative differential calculus gives us very good ways of doing that. Now, we've got two methods for identifying whether a stationary point is a max or a min. Now, you know the tables, you've seen them before, where you use the first derivative to test whether something is a max or min, or even sometimes a point of horizontal inflection. And that's nothing wrong with it, that works. But can I suggest that you take on the second derivative instead? Okay? Instead of the first derivative test, you'll need the first derivative to find, you'll still need the first derivative to find where the stationary point is. Okay, you still need that. But the second derivative is a more efficient way of finding the nature of the stationary point, as we've seen in other videos. So use the second derivative, alright, and if it's second derivative, if it's positive, you'll remember that we have a minimum, and if the second derivative is negative, you have a maximum, and if the second derivative is 0 and you can check that the concavity's changed, you have a point of horizontal inflection, all from previous videos. I'm going to show you the learning goal via an example here, and we have a small startup video streaming service. At the moment it's got 1,000 subscribers, and at the moment they're paying $5 a month, so pretty small potatoes, right, at the moment. But it's worked out it can get 100 more subscribers for each 10-cent decrease in the monthly fee. So if the monthly fee drops, we get an extra 100 if it drops by 10 cents a month. What monthly fee will yield the maximum revenue? So remember, revenue is money coming in. Okay, we're not talking about any overheads or bills or anything, or costs, all right? We're ignoring that here. We're only worried about the revenue, and revenue is not the same as profit, okay? Profit, you have to subtract all of the costs out of it and then work out what's left over. We're just talking about money coming in, okay? So we're talking about money streaming in from a streaming service. Got it? So this is a case of maximize. All right, it's an optimization question where we've got to maximize. And basically revenue, I'm going to call revenue is a function in this question. I'm going to call it R of X. Okay, so that's the revenue function. And X is I'm going to call X the monthly fee in dollars. Okay, so we've got to define our terms. You don't have to use those letters, but I'm going to use them, okay? Now, in general, in a situation like that, your revenue is going to be basically the number of subscribers you got, because they all pay a fee. So it's the monthly fee times by the number of subscribers. That's rough. That's a rough thought, okay? It's true, but that's why I like doing math symbology more than writing. I don't want to do writing too much in these videos. So we've got a term for the monthly fee. If it's the monthly fee times the number of subscribers, that's going to be X but the number of subscribers is a function too. Okay, it depends on the number of 10-cent decreases, right? So it makes it a function. So I'm going to call the number of subscribers s, lowercase s of x, because it's dependent on x as well. So we got x times some function s for the number of subscribers, which is dependent on x. So we need to work out how to come up with this function. So sometimes in optimization questions, you've got to come up with what the function is. All right, the easy ones tell you what the function is, but ones like this, you've got to manufacture or synthesize the function yourself. Haha. So we'll get this, and then we'll times it through by x to get the revenue function. Okay, so I'm going to change colors here. So to get this s of x thing, the number of subscribers function, okay, the function that describes the number of subscribers based on the number of monthly fees, all right, based on what the monthly fee is. And I just thought of something too. The more keenly aware of you may have noticed that these things are discrete. The number of people subscribing, that's a discrete quantity. And even dollars and cents, you could argue, number of people subscribing, and the dollars and cents involved, all right, they're actually discrete quantities, but in calculus, differential calculus is continuous. But we can do that, okay? We can use a continuous function in this way to model what's really discrete phenomenon. So there you go. Hopefully that alleviates any concern that you had. You can do this. So what we've got $1,000 now. All right, it said this at $1,000. That's what we started with. 1,000 subscribers, I should say, not $1,000. Okay, sorry, 1,000 subscribers. It's been a long day. 1,000 subscribers now, and we can get some extras. This is where we're encoding it from the real world into the world of maths. See, we can get more subscribers, 100 more for each of these. Okay, so we've got to turn that into a mathematical expression. So more means let's add that on, and these are going to be the extras. Okay, because S is the number of subscribers function. So extras, the extras are based on, we get 100 of them times the number of 10-cent decreases. So what we're going to do here, it's a number of 10-cent amounts that fit into it. So it's going to get divided by 10 cents. Now remember, 10 cents equals $0.1. I'm sure you remember that. That's where that comes from. Okay. Now what will happen, you see it's 5 minus X here, where X is the monthly fee. Okay. And if the monthly fee was if the monthly fee was 5, this numerator here would be 0. Okay. 5 minus 5 is 0, and you'd have 0 times 100. You'd have no extras, and you'd be back to your 1,000. And that makes sense because that's what we're given at the beginning here. All right. So that equation makes sense, and it's one of the skills involved in this optimization caper is to create suitable equations. So that might have been one of the hardest parts there to come up with that. So basically we have our, once we times it by X, we have our revenue function. So let's go back to the main part of the question. So it's X, and that's going to be, I'm going to use brackets now, the S of X, which we got over here. So it's 1,000, just grouping it all together, plus 100, putting all the other stuff in. Okay, and so we've got X outside of 1,000 plus 100 times 5 minus X over 0.1 Technically I should have a second set of brackets there. Alrighty. So I'm expanding that now, timesing by the x on the outside. I'm going to put the x here for convenience. I'm just timesing by the x on the outside, okay? Your algebra brain should be able to catch that by this stage. I probably need to straighten things up a bit, hey? All right. Now I'm doing this in baby steps. You know, some of you would probably just eat this, but you know what? Dividing by 0.1, some people forget that that's just the same as timesing by 10. So I'm putting that in. If you're super good with all of this sort of algebra I'm doing now, you know, you'll be happy to skip a couple of these steps, I'm sure, but I'm not going to do that. Okay, so we've basically just expanding the second set of brackets now to the right of each line, and I get minus 1000x squared there, 100 times 10. All right, and there's two x's and it's been minused off, and then we've got like terms, so that gives us 6000x. Yeah, again, you don't have to do all these steps, right? You're free. It's a free country depending on where you're watching this. When I say things like A, unless you're Australian or Canadian or a handful of countries, you might think that's quite odd. Hey, you know, just let me know if you're from another country. Say hello. So what we got is, after a long sequence of steps there, of very easy baby steps, we've got that. That's our revenue function, 6000x minus 1000x squared. Okay, that's revenue related to the number of monthly subscriptions. Okay, so we've got related to the cost of each subscription. Sorry, I should say. So what we need to do now, we need to find the first derivative. I'm going to call that dr dx. Okay, and then we have 6000 minus 2000x. So when we're finding stationary points, we set it equal to 0. It's only got one solution because the derivative is a linear function, and that's when x equals 3. Okay, the stationary point happens at x equals 3, so that's when the fee is $3. Now we have to check whether that is a max or a min. All right, and we're trying to maximize revenue, aren't we? So we just need to double check that. Now what I want to draw your attention to is the second derivative, the second method. It's preferred. All right, I want you to use that because it's more efficient. The first derivative test does work, it's legit, but it's slower. This is a bit more advanced, so use the second derivative test, please. So remember, the first derivative, its role is to tell us where the stationary point is, the x value that gives us a stationary point, and the second derivative, which is d squared r dx squared, tells us the nature. All right, so that tells us where, and that tells us what. Okay, so the second derivative, so the derivative of the derivative, that's negative 2000. Okay, and that's a constant, so we don't need to sub anything into that. It's always negative 2000. The point of it is that it's negative, and the negative second derivative is a maximum. So it's verified as a maximum. So conclusion time. R of x revenue function is at a maximum at x equals 3. What does that mean? Well, if we set the monthly fee, that implies that the monthly fee should be set at $3 to maximize revenue. And the question did ask us, what would that revenue be? Well, we sub 3 into the equation. All right, so we've got, instead of R of X, we've got R of 3. And if you do a bit of substitution, you get $9,000. So $9,000 for that little startup company.